So we've been working on analyzing this 3D truss. In the last video, we derived the three local stiffness matrices that correspond to element number 1, element number 2, and element number 3. At the end of the last video, I showed you this local stiffness matrix. These are the final form of the other two stiffness matrices. What I'd like to do now is to formulate or assemble the global stiffness matrix out of the information contained in these three local stiffness matrices. As you can see, each matrix has an awful lot of numerical information, and for the sake of showing you how you assemble the global stiffness matrix from the local stiffness matrices, it's not very illuminating to use the actual numerical values. So what I'm going to do is I'm going to replace these numerical values, always times this constant out in front. That, remember, that's EA over L. I'm going to replace this numeric information with variables that correspond to each matrix and each location within the matrix. So here again are our three local stiffness matrices. And for example, here, this K superscript 1 subscript 3, 2 is just a variable to replace that numeric information that was at this location in the last slide, but the superscript 1 corresponds to the fact that it is in the local stiffness matrix for element number 1, and the 3, 2 just means that it's in the third row and the second column located inside this local stiffness matrix. Okay? So I'd like to go ahead and assemble the global stiffness matrix to help understand how this information in the local matrices fits into the global matrix. It'll be easier if we multiply each one of these matrices by the local displacement vector that we normally multiply a local stiffness matrix by. So you'll remember that I'm going to multiply this matrix by, since element number 1 corresponds from node 1 to node 2, node 1, of course, has a displacement in the x, y, and z direction, u, v, and w. I will multiply this matrix by u1, v1, w1, u2, v2, w2. And to make it easier for us to place each different member of this matrix into the global matrix, I'm also going to lay this vector on its side along the top to serve as column headers. So we'll have u1, v1, w1, u2, v2, w2. I'm going to go ahead and do the same thing for the other two matrices. Matrix number 2 corresponds to element number 2. Element number 2 connects node 1 to node 3. So here, my local displacement vector will be u1, v1, w1, u3, v3, w3. Along the top, I'll also have u1, v1, w1, u3, v3, w3, and matrix number 3 corresponds to element number 3 that connects node 1 to node 4. So I'll have this multiplied by u1, v1, w1, u4, v4, w4. And along the top, u1, v1, w1, u4, v4, w4. Okay? Now, I'm going to take this information, and the reason, of course, we did this is to make things easier when we form the global stiffness matrix. How big does the global stiffness matrix need to be? The way to calculate that is to realize that each node has 3 degrees of freedom. Each node can move in the x direction, the y direction, the z direction. That's 3 degrees of freedom. There are 4 nodes, 1, 2, 3, 4. 4 nodes with 3 degrees of freedom each means that our global stiffness matrix will need to be a 12 by 12. Okay, so here I've placed a table to represent our global stiffness matrix, and like I did for the local stiffness matrices, I have column headers and row headers that let me know what degree of freedom corresponds to what column and what node. Now all I have to do is look at what degree of freedom each row and each column represents and place each member of each matrix in an appropriate column and row in the global matrix. And we've done this for a one-dimensional case, and we've done this for the two-dimensional case. So you should be kind of getting used to this by now. You can do this element by element or member by member. That will take quite a long time and a bit of thinking. For this first matrix, you should be able to realize that since this U1, V1, W1, U2, V2, W2 is the same as these columns here, and these rows are the same as the first 6 rows here, that I can just take this matrix and it should go very nicely into the upper left-hand quadrant of my global matrix. Now, you might think that I could do the same thing with the other two matrices, but you have to think a little bit. Here I have U1, V1, W1, but here I have U1, V1, W1. So I can take the submatrix, which represents these 9 elements, and place them in these 9 elements here. Remember, summing with the values that are already there. As I go to the next, however, I'll notice this corresponds to U1, U3, V3, and W3. So I can't put them here, here, and here. They'll go into this space here. Likewise, I can continue with the other two quadrants of my K2 matrix. And once I start recognizing the pattern, I can go ahead and do the same logic to the K3 matrix. All right? Now, there's a lot of elements that don't, or members of my global stiffness matrix that have no value. I'll just go ahead and I'll fill those in with zeros. So now this forms my global stiffness matrix. In the next video, we will apply boundary conditions and write this as a matrix rather than just a table.